Section 9.3 is the Pythagorean Theorem. I can use the Pythagorean Theorem to solve problems. In a right triangle, the hypotenuse is the side opposite the right angle. So again, in a right triangle, right angle here, the side opposite of that is our hypotenuse. The legs are the sides that form the right angle. So this is a leg and this is a leg. The lengths of the legs and the length of the hypotenuse of a right triangle are related by the Pythagorean theorem. So, for any right triangle, the sum of the squares of the lengths of the legs equals the square of the length of the hypotenuse. A squared equals B squared plus, A squared plus B squared equals C squared. In example 1, we're going to find the length of the hypotenuse of a triangle if the side lengths are 212 feet and 478 feet. So to find the length of a triangle, if we're talking about a hypotenuse here, we're going to use Pythagorean theorem. A squared plus B squared equals C squared. Again, our side lengths are A and B value, and it doesn't matter which one we plug in where as far as our sides go, but what does matter is our hypotenuse always has to be C. So for A, I'm going to plug in 212. Don't forget we have to square it. And for B, I'm going to plug in 478. And again, don't forget we have to square it. Now to simplify here, I can take 212 and square it. And then I can take 478 and square it. For 212, I get 44,944. And 478 squared is 228,484. And I square them before I add because of PEMDAS. PEMDAS says we do any parentheses first, then exponents. Multiplication and division if we have any, here we don't. And then we can add and subtract. So when I add those together, I get 273,428. And that's what C squared. So that's the square of my hypotenuse. But I'm not looking for the square of my hypotenuse. I'm looking for the hypotenuse itself. I'm looking for what number did we have to square to get to here. So to get rid of our square, guys, we take the square root of both sides. I'm looking for the square root of C squared, the square root of 273,428. And when I take the square root of that on my calculator, I get 522.9 approximately for C. And since my sides are in feet, so is my hypotenuse. So the hypotenuse is approximately 522.9 or 523 feet if we're talking significant figures. In example 2, we want to know the missing length A in simplest form. So here we want to keep it in terms of radicals, in terms of square roots. So A squared plus B squared equals C squared. That's our Pythagorean theorem. I don't know A, that's what I'm looking for. So I keep my A as just an A. I know B is 10. I plug that in for B and square it. And I know C is 12. So I plug that in for C and square it. Now again, according to PEMDAS, we have to do our exponents first. I can't do anything with my A, but 10 squared is 100. And 12 squared is 144. Now, both sides of my equal sign are as simple as I can get them, so now I can start solving for my variable. In order to get A by itself, I have to get rid of the 100, and it's being added, so here I subtract it to move it to the other side, so that the only thing I have on one side of my equal sign is my variable. Here, I get 44. Again, to get rid of a square, we take the square root. We're looking for what number would we have to square to get to A. We want the square root. What number did we square to get to 44? Here, the square root of 44, we have to reduce. They want it in simplest form. So I'm going to take and make a factor tree here. 4 times 11 and 2 times 2. So I'm going to rewrite the square root of 44 as the square root of 2 times 2 times 11. Now, I look for any groups. any pairs. Here I have a pair of 2's, so I can take that out as a set of 2. Remember, 2 times 2 is 4, and when I take the square root of 4, I get 2. So outside, I've used those 2's. I have a 2. Inside, I still have an 11 that we haven't used. So the square root of 44 simplifies to 2 square roots of 11. Anything without a pair stays inside. Anything with a pair goes outside as a pair of 2's, so we just write it as a 2. If you're not sure if those are the same, you can take the square root of 44, which is approximately 6.6, and you can take 2 times the square root of 11, which is approximately 6.6 as well. Again, if we wanted to check this too, we could take our answer and plug it back into our original formula. So I can take 2 times the square root of 11 squared plus 10 squared gives me 144. And I know that's what c squared is as well, so I know that my answer is right. Feel free to pause here and give this a try if you'd like. We're going to find the unknown length and write the answer in simplest form. So here, a squared plus b squared equals c squared. That's Pythagorean's theorem, and we use it for side lengths of right triangles. A is 20, so a squared plus, I don't have a b, so I leave it as a b. And c squared, c is 25 squared. So here our first step is to get rid of our exponents. We don't have any parentheses according to PEMDAS. We would do those first. Here we don't have any. 2 squared is 4, but it's not 2, it's 20. So we have to factor in those zeros. Account for those. 25 squared is 625. Now, we've simplified our left side as simple as we can get it, and we've simplified our right side as simple as we can get it. We have to try to solve for b now. To get our b by itself, right now we're adding 400. I get rid of that 400 by subtracting it. Again, we're trying to get it so that there's nothing added on to b. 400 minus 400 is how I get to 0. So I just have b squared equals 225. We're looking for what number did we square to get to 225. So in order to find that, we take the square root. And I get b equals the square root of 225. 225 is 5 times 45, which is 5 times 9, which is 3 times 3. So here, keep in mind, square root of 25 is still in a square root. I have 3 times 3 times 5 times 5. I look for any pairs. I have a pair of 3's, those come out as a 3. I have a pair of 5's, those come out as a 5. And now I've used those, so I take 5 times 3, 15, and I don't have anything left inside my square root, so I don't need to write a square root at all. Here I get 15. We also could have checked the board to see if 225 is a perfect square. It is, so then we know that it's 15. Same idea here for number 2. A squared plus b squared equals c squared. We're going to plug in our values. A is 10 squared plus b is 24 squared equals c squared. So again, we're going to get rid of our exponents first. 10 squared is 100. 24 squared is 576. Now we have to simplify each side before we can solve. So on the left-hand side, we can add those up and get 676, and that equals c squared. We don't want c squared though, we want to know what is c. So we want to know what number did we have to square to get to 676, which means we're going to take the square root. Here we can check to see if it's a perfect square. We don't have it on our board, so it's not a perfect square less than 20, but we can check in our calculator. If we take the square root of 676, I get 26 even. And since I get exactly 26, I can do that. We don't want to have a decimal approximation. So if we would have had a decimal, we'd have had to break it down like I did up here with the 225. Okay, to reduce it. But since the square root of 676 is just 26, we can go ahead and use our calculator there. Here, a squared plus b squared equals c squared. A we don't know, b is 12, and c is 14. So again, our first step is to simplify anything that we can. 12 squared, 144. 14 squared, 196. We can't simplify on the left anymore, we can't simplify on the right anymore, so now we try and get our variable by itself. It's being added on by 144, so I'm going to go ahead and subtract 144. And I get 52. Now we're looking for what number did we square to get to 52, so I'm going to take the square root of both sides and the square root of 52. Keep in mind we do still have to reduce that. So here I'm going to take 52 and break it down into 4 times 13, which is 2 times 2. So I'm going to have the square root of 2 times 2 times 13. I have a pair of 2's, so I can take that out. And I'm left with a 2. Inside my square root, I have a 13. So a is going to be 2 times the square root of 13. The converse of the Pythagorean theorem says that if a squared and b squared equals a squared plus b squared equals c squared, then the triangle has to be a right triangle. So we can use this idea to check and see whether or not measures will give us a right triangle. So a squared plus b squared equals c squared. We take our largest side, our longest side, and that is always our c. So here they're labeled, but if they weren't, we would still know that's our c, our hypotenuse, because it's the longest side. We simplify. 3 squared is 9, 5 squared is 25, and 7 squared is 49. Add them up and we get 34 equals 49. Since 34 does not equal 49, the Pythagorean theorem is not right, and means that it's not a right triangle. Okay? If it's not a true statement with our Pythagorean theorem, then it is not a right triangle. We can try it again here for b. A squared plus b squared equals c squared. Again, both sides have to be the same in order for it to be true. 15 squared plus 8 squared equals 17 squared. 15 squared is 225. And 8 squared is 64. 17 squared is 289. Simplify here by combining our like terms. We want to have each side as simple as we can get it. So we're going to add these up and get 289. So since 289 does equal 289, it means that our Pythagorean theorem is true here, which means yes, this would be a right triangle. And again, keep in mind our biggest side length is always our c, that's our hypotenuse. So if we plug our values into Pythagorean theorem and it gives us a true statement, then it is a right triangle. If it doesn't, then it's not. And that's all I have here for section 9.3.